What If Light Had Mass by Adam Majara, Anay Durgut, and Leon Dolan. So here are some parameters for our project, the most important of which being that the mass of a photon is assumed to be equal to the mass of an electron. Modeling massive photons. In our first model, we state that the total energy of a massive photon is equal to the sum of its kinetic energy and gravitational potential energy in relation to the Earth. We assume that the energy is equal to that of massless photons, which is E equals hf. And using these formulas, we get this model right here. We can find the frequency associated with our top speed by assuming that gravitational potential energy is 0. And upon calculating, we find that the frequency is about 6.183 times 10 to the 19th hertz. This poses a problem, because special relativity states that no massive object can move at the speed of light since this requires infinite energy, and our photon requires just 4.1 times 10 to the negative 14th joules to move at this speed, which contradicts special relativity. From this, we can also concur that E does not equal hf for massive protons. Another model we can use is the energy-momentum relation, and it relates total energy to rest mass, where massless protons are E equals hf, but massive protons are this model right here. So if we have a massless and a massive proton with the same frequency, we can find the energy for both of them. A massless proton would be E sub 1, which is equal to 3.315 times 10 to the negative 19th joules. And we are assuming that their momentum is equal to each other, so we can calculate the momentum for our massless photon. For a massive photon, we have the momentum and the mass, so we can calculate that its energy is about 8.199 times 10 to the negative 14th joules. And from this, we can see that massive photons with the same frequency carry more energy than massless photons.
So now we're going to talk about macroscopic interactions and impacts that will result from photons having mass. One major impact would be a new relationship between light and gravity. In the real world, a photon both exerts a gravitational force due to it having energy and there being a mass-energy equivalence, and is subject to gravitational influence. However, it's important to note that because photons are massless, they're not directly impacted by gravitational forces. They simply follow curves in spacetime that are caused by objects with gravitational fields. And a photon having mass would increase both the gravitational field it exerts and the gravitational force exerted on it. An increased mass would mean increased energy and gravitational field of the photon, which would mean an increased gravitational force exerted on nearby objects. And the gravitational force exerted on it would increase from nothing, because there was no mass before, to a non-zero number, as there would now be a mass for the force to be exerted on. Another thing that would be impacted would be our ability to use absorption spectra to tell elemental composition. Giving a photon mass would, as I said, increase its total energy, and a change energy level of photons would impact the frequencies of light that could be absorbed by electrons in certain atoms, which would impact the absorption spectra. And if we weren't able to properly account for this change in photon energy, it would severely harm our ability to determine things such as the atmospheric composition of distant planets or the makeup of stars, which would limit our ability to learn about our universe. So what are the physical implications of light actually having mass? First of all, light would now have pressure, as it applies a force when it hits things. The pressure of the light would be based off its mass, velocity, and the intensity of the photons. This would give light a much greater impact on objects around it than it does in the current world. This could be used for many technological advancements, and if it was concentrated enough, it could even become a lightsaber. Due to the conservation of energy, every time photons collide with each other, they would lose some of their speed as their kinetic energy would be converted. After enough collisions, the photons will have lost most, if not all, of their kinetic energy, and some would become stationary. And then gravity would pull the stationary photons to the ground, leaving a floor of photons. These photons would not be visible unless you move your eye into them, and that would mean a room would get darker as the speed of the photons decreases, which could be reversed by increasing the kinetic energy of the photons. Since light no longer has a constant speed, different objects would take different photons would take different amount of times to reach your eyes. This means multiple different images from different times could be seen at the same time. This is similar to how we can see back in time, because the universe is so long and that so big, and the light speed is not infinite. However, this would be much more evident and be impactful on a smaller scale. Two objects that are the same distance could be perceived at different times if their photons are traveling at different speeds. This could be imagined with abstract art, which paints different parts of the picture at different times. So it's kind of fusing different times at the same time, which is what you might see. And if an object is releasing photons that increase in speed at the correct rate, it could lead to you seeing two images from the same object at the same time. Thank you. That's it.